All right, let's jump right in. Have you ever had two different pieces of info that just don't seem connected? Well, in algebra, there's a really powerful way to find exactly where they meet. We're talking about solving systems of linear equations. And really, at its core, it's all about finding that one single point of truth, where two different stories, or in this case, two lines on a graph, actually cross paths. So let's break down this absolutely foundational skill.
So what's the game plan? First up, we're going to get a really clear picture of what a system even is and what we're trying to do. Then we'll build up our toolkit with 3 different methods. We've got the visual approach with graphing, the kind of clever swap out of substitution, and the powerhouse method of elimination. And to wrap it all up, we'll see how this stuff actually applies to real-world problems and, this is key, how to pick the perfect tool for the job.
All right, first things first. Let's define what we're actually dealing with here. So before we even think about solving anything, what exactly is a system? Honestly, the best way to think about it is like a logic puzzle. You're given 2 clues. For us, that's 2 linear equations. And your mission is to find the one and only pair of numbers for x and y that makes both of those clues true at the exact same time. On a graph, this is super visual. Each equation is just a straight line. So our solution, the answer to the puzzle, it's literally the exact point where those 2 lines cross over each other. Okay, so finding one point where 2 lines cross. That seems pretty straightforward, right? But hold on a second. Is that really the only thing that can happen when you draw 2 lines on a page? Think about it. Well, it turns out there are actually 3 possibilities. The one we see most often is on the left, an independent system. That's just 2 lines crossing at one single point. Boom. One unique solution. But then, in the middle, you've got an inconsistent system. See how the lines are parallel? They have the same slope, so they're just never ever going to touch. That means no solution. And finally, on the right, we have a dependent system. Now this one's tricky. It looks like one line, but it's actually 2 different equations that describe the exact same line. They're right on top of each other. So how many solutions? An infinite number of them. And this leads us to the golden rule, the most important thing to remember. A solution has to work for every single equation in the system, no exceptions. So let's look at this example. We're testing the point 8, 5. We plug it into that first equation, and yeah, it works perfectly. We get 20 equals 20. Great. But when we plug it into the second equation, we get 17 equals 15. No, that's totally false. And because it failed just one of the tests, we know for sure 8, 5 is not the solution. Okay, so now we know what a solution is and what it's supposed to do. The big question is, how do we find it? Let's start with our first method, which is probably the most intuitive one, the visual approach of solving by graphing. The process here is just so simple, it's almost beautiful. Step 1, you graph the first line. Step 2, you graph the second line on the very same grid. And step 3, you just look, you find the point where they cross. In this example, you can see it plain as day. It's right there at 0, -1. That's it. That's our solution. Now, graphing is awesome for getting a picture of the problem, but it does have a weakness. If the answer is something messy, like with fractions or decimals, it can be really, really tough to get the exact answer just by eyeballing it. So, when we need that pinpoint accuracy, we have to turn to algebra. And that brings us to our second method, the strategic tool we call substitution. Substitution is basically a 4-step recipe to solve the puzzle. Step 1 is isolate. Your goal is to get one variable, let's say x, all by itself in one of the equations. Step 2 is substitute, and this is the magic move. You take whatever x is equal to and you plug it into the other equation. It's like a swap out. And the whole point is to create a new equation that only has one variable. Step 3, solve that much easier equation. And finally, step 4 is back substitute. You just take the number you found and plug it back into one of the original equations to find the value of the other variable. Done. Okay, let's see this recipe in action. In this example, step 1 is actually already done for us. How nice is that? The first equation flat out tells us that x is the exact same thing as y plus 10. So we jump right to step 2. We substitute. We take that y plus 10 and we drop it into the second equation right where the x was. And look at that. Now we have one simple equation with just y in it. We solve it and we get y equals -5. To finish up, we just back substitute. We plug that -5 back in for y, and that tells us x equals 5. And there's our solution pair, 5, -5. Okay, but let's be real, it's not always going to be set up that perfectly for us. In this example, we have to do step 1 all by ourselves. But if you look at that first equation, it's actually pretty easy to get y alone, just by adding x to both sides. That gives us y equals x minus 5. And from there, the process is exactly the same. We substitute this into the second equation, solve for x, and then use that answer to find y. See? The core strategy doesn't change a bit. All right, time for our third and final method. And let me tell you, when your equations are all nice and lined up, this is the one you want. I like to call it the power tool, solving by elimination. The absolute beauty of elimination is how systematic it is. First, you align your equations, stacking them right on top of each other. Second, you modify one or both of them. This means you multiply an equation by some number to make the coefficients, the numbers in front of the variables, perfect opposites, like a positive 5x and a negative 5x. Why? Because of step 3, eliminate. You add the two equations together, and those opposite terms just cancel each other out. They're gone. Finally, you solve for whatever variable is left, and then find the other one, just like before. Let's watch the magic happen. Okay, so our goal here is to get rid of the y variable. To make those coefficients opposites, we can just multiply that whole top equation by -2. See what happens? The -5y turns into a plus 10y. Now when we add the two equations straight down, poof, the y terms completely vanish, they cancel out to 0. We're left with a super simple equation to solve for x, and we find out x is -8. One quick plug-in later, and we get y equals -5. Now, this method works brilliantly when you can knock out one variable. But what happens if you go to add the equations together and poof, both variables disappear? What does that mean? This is where we circle right back to those special cases we saw earlier. If you eliminate the variables and you're left with something that's always true, like 0 equals 0, that's the math's way of telling you that your two equations were just two different ways of describing the exact same line. That's a dependent system with infinite solutions. But if the variables vanish and you're left with something totally false, like 0 equals 5, well, that's a flat-out contradiction. It means you were dealing with two parallel lines that were never, ever going to cross. That's an inconsistent system, and it has no solution. So, okay, we've got all these awesome algebraic tools. But what's the point? When are you ever going to use this? How do we take a messy, real-world problem and turn it from just a bunch of words into something we can actually solve with math? This is where it all clicks into place. In so many real-world problems, you're looking for a simple pattern. There's usually one clue about how many of something there is, the quantity, and another clue about how much it's worth, the value. Check out this smoothie shop problem. The quantity equation is super simple. The number of pineapple smoothies plus mango smoothies equals 60. Then the value equation just uses the prices to add up to the total money they made. And just like that, you've turned a word problem into a system that you know exactly how to solve. And believe me, once you see this pattern, you'll start seeing it everywhere. Look at this one with bus tickets. Same deal. We know the total number of tickets they sold, and we know the total amount of money they brought in. That first fact gives us our quantity equation, x plus y equals 32. The second fact gives us our value equation, using the ticket prices. We build the system, we turn the crank on one of our methods, and we get the answer. They sold 7 senior tickets and 25 regular tickets. Okay, we've built this amazing toolkit with 3 totally different methods: graphing, substitution, and elimination. But this leads to the most important strategic question of all. Which one should you choose and when? Here's your cheat sheet for picking the right tool for the job. You should use graphing when you just need a quick visual guess and the answer looks like it's going to be a nice, clean, whole number. You should go for substitution if you see a variable that's already all by itself or looks super easy to get by itself. And finally, elimination is your absolute best friend when both equations are already lined up perfectly in standard form. For that setup, it is by far the most powerful and efficient tool you've got. So at the end of the day, it doesn't matter if you're using graphs, substitution, or elimination, never lose sight of the ultimate goal. You're not just mindlessly crunching numbers, you are on a hunt for a single point of consistency. That one singular answer that makes every single clue true and brings the whole system into perfect balance. The only question left is, what problem are you going to solve with this?